Hello, my name is Jordan Santorsula. I'm a Master of Applied Science student at York University. In collaboration with my thesis supervisor, Dr. Liam Butler, today I'm going to be presenting our research paper, The Preliminary Review and Experimental Assessment of Low-Carbon Concrete Produced with Recycled and Supplementary Materials. Now, a little bit of background. Concrete is the most widely used construction material in the world, with over 10 billion tons produced annually. Now, these volumes are generally produced using natural coarse and fine aggregates, water, and ordinary Portland cement. The problem is that the overwhelming use of concrete has led to the widespread degradation of many global environmental systems, extensive generations of greenhouse gases and carbon dioxide emissions, specifically from cement, while many regions lack concrete reutilization and recycling programs to deal with the extensive amount of concrete demolition waste generated annually. Now, to emphasize these points, I have two pictures of Toronto, Canada from 1974 and to 2014. Now, within this 40-year period, you can see that extensive infrastructure development has occurred, which means extensive use of concrete, while the extensive infrastructure development also means the tearing down and demolition of the previous buildings to make way for the new buildings, resulting in the billions of tons of concrete and demolition waste. Now, this poses the two problems I mentioned, extensive use of concrete and an overwhelming generation of waste. Now, in an effort to find a solution for all of this, many researchers have focused on the use of low-carbon concrete produced with recycled concrete aggregates, or RCA, and supplementary cementitious materials, or SCMs. Preliminary studies have found that RCA and SCM usage often leads to reduced or highly variable mechanical properties, and this poor mechanical performance has often led to a lack of established design standards in industrial usage, and further research incorporating higher volumes of RCA and SCMs despite their sustainability benefits. Novel mixture design methods have been utilized to improve the properties of low-carbon concrete. However, a detailed analysis regarding the effect of these methods, the low-carbon concrete usage within these methods, have not been conducted. Now, this brings us to our research objectives, which we divided into two stages. The literature analysis consisted of the analysis regarding the low-carbon concrete material usage and novel mixture design methods, as well as the effect of these materials and mixed design methods on the mechanical properties of low-carbon concrete. The second stage was an experimental mixed design, which consisted of investigating the effect of coarse and fine RCA, SCMs, and novel mixed design methods on the mechanical properties of low-carbon concrete. Should be noted that no durability testing was conducted as part of this preliminary testing. Starting with the literature analysis, in terms of mixture material usage, it can be seen that the majority of studies have utilized coarse RCA, shown in blue, with over 74% of the studies, while minimal studies have utilized FRCA, coarse and fine RCA, and RCA plus SCMs in any capacity. There has also been a lack of studies utilizing high RCA and SCM usage, given the negative effects on the mechanical properties of low-carbon concrete. In terms of the effect on the properties, we have four plots here. The top plots show the effect of coarse RCA and fine RCA content on the compressive strength values, while the bottom plots show their effect on the splitting tensile strength properties. The findings indicate that increasing fine, coarse RCA and SCM content reduces the compressive and tensile strengths. Many of these reductions are attributed to the water absorption properties and microstructure complexities of the RCA sources, the slower strength development properties of SCMs, as well as the lack of specific design standards for the production of low-carbon concrete. However, based on the results, mixtures using fine RCA with content of over 75%, or mixtures with 100% coarse RCA and 40% SCMs have been able to achieve compressive strengths exceeding 35 MPa and tensile strength exceeding 3 MPa, indicating the structural capacities of these concrete mixtures. Now, moving forward in the literature analysis, in terms of mixed design methods, we focus on two different methods. Mixing methods, which have been utilized to improve the microstructure characteristics, as well as the durability and mechanical strength properties of mixtures incorporating RCA, and then mixture proportioning methods, which have utilized the properties of RCA sources effectively within the mix design to improve the fresh and hardened properties of the low-carbon concrete mixtures. Now, within each of these, we focus on two different methods. Within the mixing methods, we focus on double mixing and two-stage mixing, while in the mixture proportioning, we focus on equivalent mortar volume and modified equivalent mortar volume proportioning. In terms of the mixture proportioning methods, it was found that the use of the equivalent mortar volume and modified EMV methods improved the compressive and tensile strength values and predictability as per the water to cement ratio and binder content of these mixtures. It was also found that these EMV-based mixture proportions reduce the cement and binder content relative to the mixture's proportion with the conventional mix design methods. However, it should be noted that these mixtures often display low workability values. It should be noted that the existing studies utilizing the equivalent mortar volume-based mixture proportionings have only been limited to coarse RCA mixtures. The use of fine RCA or SCMs have not been included or have been limited to very small percentages under 30%. In terms of mixing methods, it was found that the two-stage and double mixing methods resulted in up to 17 and 21% higher compressive and flexural strength values, while scanning electron microscope analysis also found that these methods improve the microstructure characteristics, strengthening the aggregates and filling in cracks and voids within the RCA structure. However, it was noted that the two-stage and double mixing methods have received minimal research attention, with further research required to assess their effect with high volume replacements of low carbon concrete materials. Now, based on the findings from the literature review, this brings us to our experimental program. Now, the purpose of our program was to investigate the combined effect of using high RCA and high SCM contents with novel mixture design methods, specifically the modified EMV and two-stage mixing approach. Now, our mix design program was split into two separate sections consisting of a low and high strength mix with a target strength of 30 MPa and a target strength of 50 MPa. The mixture characteristics of the two mixtures are shown in the table provided. In terms of the material properties, starting with the aggregates, it was found that while the RCAs were produced in a different manner compared to the natural aggregates, the RCA were able to meet the structural concrete gradation limits. However, in terms of the properties, the RCA had significantly higher absorption capacity, lower bulk density, lower bulk specific gravity values, and lower abrasion resistance values relative to the natural aggregate sources. It should be noted that the higher absorption properties and as well the lower density values of the RCA sources is attributed to the residual mortar fraction within the recycled concrete aggregates. Now, moving forward, the mixture proportions for the concrete mixtures are provided in the table below. It should be noted that the mixtures were proportioned for target slumps of 100 MPa plus or minus 25 MPa. They were also cast into cylindrical specimens with a diameter of 100 millimeters and a height of 200 millimeters. All the specimens were demolded after 1 day and moist cured until testing. However, it should be noted that given the absorption capacity of the aggregates, additional water shown in the table with water with the subscript B were added to each of the mixtures given the air-dried moisture content of the aggregates. In terms of fresh properties, it was found that the RRS mixtures, or the mixtures proportioned with the conventional mix design methods, presented higher slump values, while the mixtures proportioned with the EMV-based method, so the RRS-M mixtures, presented slump reductions. The higher slump values of the first set of mixtures was attributed to the increased free water content, as well as the effect of the CSA mixing methods, consisting of the simultaneous mixing of all materials, resulting in the filling of the pores and lack of water absorption by the aggregates. While in the RRS-M mixtures, the reduced free water content of the modified EMV-based mixture proportioning and effect of the two-stage mixing approach, consisting of the separation of the water and the cement content, allow for further absorption, reducing the free water content and workability of the mixtures. It should also be noted that the slump values were also impacted by the particle fineness of the slag sources, as well as the interparticle friction and increased angularity of the RCA sources. In terms of the hardened concrete properties, the values for the various mixtures are provided in the table. In general, it was found that in terms of compressive strength, both the mixtures, regardless of their mixture design method, had similar values, with up to a 54.8% reduction, regardless of the target strength class. In terms of tensile strengths, the mixtures proportioned with the conventional mix design methods displayed reductions up to 43.3% relative to the control mixtures, while the two-stage mixing and EMV-based mix design mixtures only presented reductions up to 31.5%. Based on the results, it can be found that the use of the modified EMV and two-stage mixing approach led to a more sustainable choice, as they achieved similar mechanical strength properties as the conventional mix design methods, even improving the tensile strength values, while reducing the binder content with a maximum binder reduction of 66.1 kilograms per cubic meter of concrete. In summary of the experimental findings, the low strength class, regardless of the mixture design method, were able to achieve compressive strengths of over 15 MPa and tensile strengths with 2 MPa while using 100% coarse, 100% fine RCA and 50% slag, while for the high strength mixtures, regardless of mixture design, structural grade concrete with compressive strengths over 25 MPa and tensile strengths over 2.5 MPa were achieved while using 100% coarse and 100% fine RCA and 50% slag. Now, to conclude everything, going back to the literature analysis, Low-carbon concrete or CRCA have been extensively studied in research, while the use of fine RCA, coarse and fine RCA, or RCA with SCMs have received minimal research attention. However, despite the reductions observed within many research studies, the use of recycled concrete aggregates and SCMs have been able to produce concrete with compressive strengths over 50 MPa and tensile strengths over 3 MPa. As well, literature analysis also found that novel mix design methods can help reduce mechanical strength variability and reduce the overall binder content of the mixtures. To sum up the experimental program, in terms of fresh properties, the CSA design mixes led to higher slump values, while the EMV and two-stage mixing approach mix design methods led to lower slump values. In terms of hardened concrete properties, the use of 100% coarse, 100% fine, and 50% slag led up to lower compressive strength values, up to 55% lower, tensile strength reductions up to 43%, regardless of the mixture design method. It should be noted that the CSA mixed design methods led to lower tensile strength, with reductions up to 43.3%, while the use of the EMV and two-stage mixing approach led to minor reductions, with only 31.5% reduction observed. In terms of sustainability, it should be found that the modified EMV and two-stage mixing approach utilize much lower binder contents compared to the CSA mixed design methods, while having minimal effect on the mechanical strength properties and even improving tensile strength properties. In terms of future studies, it is recommended that the durability assessment of low-carbon concrete using 100% RCA and high slag or SCM contents be conducted in future studies. It's recommended that they investigate the suitability of these low-carbon concretes in further exposure conditions and applications, such as under freeze-thaw exposure, exposure to de-icing chemicals, and seawater. Now, before I conclude my presentation, I would like to acknowledge the staff at the Lisbon School of Engineering at York University for their assistance, the National Science and Engineering Research Council of Canada for funding the research, and as well CRH for generously donating materials. As well, I would like to thank the FIB Lisbon Symposium 2021 organizers and reviewers for organizing this conference and allowing us to participate. Additionally, I would also like to thank the viewers for watching my presentation, and as well, I encourage you to get in touch with any questions, comments, or future research collaborations. Thank you, and I hope you enjoyed.